Okay, so this is my PowerPoint presentation on A-star. Yeah, so let's just dive right on in. So the A-star algorithm by Jeffrey Belcher, or your narrator is Jeffrey Belcher. So to understand what the A-star algorithm is, you kind of need to understand what an algorithm is. So what we have here is the definition of an algorithm. It's a process or a set of rules to be followed in calculations or in other problem-solving operations, especially by a computer. The algorithms these days are almost always executed by computers. We're talking about huge algorithms that calculate like massive probabilities and whatnot, or like tiny little algorithms like your morning routine. There's an algorithm everywhere, but for this we're going to be talking about computer algorithms. A simple example of an algorithm is just like a flowchart like this of a daily task. Your laptop isn't turning on? Well, does pressing the power button turn it on? If it's yes, then the laptop turns on. But if it's no, then you have to check, is it a battery? If it is, then yes, plug it in, and then we go to another check. If it's not, then go to IT. If we plug it in and turning it on works, then yeah, it works. But if it doesn't, then no. So, easy to see. Just like an algorithm, you have your checks, your commands, and your results. So, yeah, this just shows how an algorithm is kind of just there in everyday life. A more complicated algorithm would be something like this, where like a corporation has like a flowchart to see what happens when something goes down or some sort of accident happens. Yeah, like it gets more complicated, but that was just a simple example. So yeah, the A-star algorithm. The A-star algorithm. It's a pathfinding algorithm. What that means is we're trying to find the easiest way, or the shortest path between point A and point B, using these nodes, and this algorithm essentially lets us, or shows us the shortest path there. So you might be wondering, how does this work? How does a computer know how to do this? Because teaching a computer to do this it's like teaching the biggest idiot on the planet how to find the shortest path between. That's what my dad always said. It's like teaching the biggest idiot how to do something. Because computers don't really know what they're doing. They're just really obedient and quick. But they have no skills. So, you need to teach them with code, essentially how to do this. So the code is in the other video, but this is just the logic behind it. And, yeah. So, A-star uses two things. It uses lists and nodes. As far as lists go, it uses something called an open list and a closed list. Basically, I'll explain that when we hit the visual, but all you need to know right now is that an open list is nodes that need to be checked, and closed list is nodes that have already been checked. And you're probably saying, oh, what's a node? Well, we have a little... here's a node, essentially. We have a grid here. A node is basically any square in between. For A-star purposes, it's like this. So like this is a node, this is a node, this is a node, this is a node, this is a node. Like everything's a node. A node, they all have common characteristics. They have an h-value, which is the estimated distance to the target node. It's a pathfinding algorithm, so you kind of need to know where you're going or where you want to end up. So that's the estimated cost. The g-value is the cost to move to another node. Generally, if it's a horizontal or vertical movement by 1, it is 10. And if it is a diagonal movement from one node to another, then it's 14. The f-value is just the heuristic plus the g. And this is used to essentially find the smallest one. The smallest, it's used to narrow down the nodes that you need to look at, because we don't want to check every single node. We just want to check the nodes that are relevant if you will. The parent node. A parent node is essentially just something that it's way easier to explain the visual, so I'll just wait till that. Passable. Is it passable? Can I actually go through this node? That's an important one. And then coordinate. Not necessarily. You wouldn't really need this on like a grid, but you would need it on a grid, but you wouldn't really need it if you're looking at like a railroad stops or like roads, and that's just kind of in applications. But in this situation on a grid, we're going to want pair coordinates. Excuse me. So here's a quick animation. We might as well explain open lists and closed lists now, and just kind of what's going on here. The start node is right here. In this animation, the start node is right here. And the target node is here. Anything in red cannot be passed. And these arrows, you're probably saying, oh, what's these arrows? That's what a parent node is. So basically how the algorithm works is that you take the node, or the starting node, you check the surrounding 8. You basically make all those 8 have the parent node of the starting one. And then, you just keep going. So you check all these. Right here, see these values here in the top right of each node? Those are the heuristic costs, the H values. And the G values are right here in the blue. So if we look in this example, what you end up doing is you calculate the F cost for every single node that hasn't been checked, which would be on the open list. And then once you check it, you put it on the closed list and keep moving on. And how do you know which one to pick? Well, you pick the one with the lowest F cost. That's why we have an F cost. So we have 27, so one of these will be picked, will be checked at some point in this animation. So this one was picked first, and then that one, because that was the lowest cost. And then we look through here. So 29 looks to be the one. Also, which one he picks? So he picks that one. And he picks that one. So we look through here, 33, 31. 31's the lowest right now as we look through them. Yep, 31, so he's gonna choose that one. See? And then second lowest, 33. Oh. Third lowest, or now we're at the 34, I think. Yep. Then he's gonna probably check 36. One of these two. Pick 36. What's the lowest one now? 36 here, so it checks that one. Lowest one is 39. Or, no, it wasn't. Oh, 39. So here. And we found it. And then, the beauty of it is that we end up being able to trace back through the parent nodes all the way back to the starting node, and that's where you get your path from. That's how you get your path. That's how you get the shortest path. And that is actually, when I figured this out, it was genius. I was like, wow, this is amazing. So, so see, you just follow the parent nodes all the way there. So you start here, boom, 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 boom. It's really efficient, and it saves a lot of computing power. So the applications of this, you can probably see how this might be useful. It's really popular in the gaming industry right now. Very, very popular. Especially in like zombie games like this, like where the zombies or the AI needs to find the quickest the route to you, just to make it realistic. They would calculate that. Railroad, there's an animation on Wikipedia of the railroad of North America, and like A start pathing it. And you could also do this on the roads. A GPS could use A star to find the shortest path. And if you deselect highways, you just change the Boolean is passable on those nodes, and now boom, they're not passable, so it just keeps moving on. And it's a really nice algorithm. So yeah, the code's in the other video. So I'd check that out. Here's hopefully this PowerPoint gives you a bit of logic before we hop into the code. Yeah. So thank you very much.